Welcome to this skill session. A skill session is our custom webinar format for our communities at Gerlent, German talent, and Glolent, global talent. More info on gerlent.com and glolent.com. Enjoy.
Okay, thanks again, Eve, for giving this presentation about Hadoop. Eve has been a data scientist for the past years and is an expert on security and data science. And maybe you can introduce yourself.
Sure thing. Should I just take it on from here in that case?
Yes, exactly. You can take it.
Okay, cool. So, first of all, thank you everybody for joining. Thank you also for the opportunity to present to Gerlent community. I guess you're here because you're keen to be introduced to Hadoop technology. And in fact, this is was going to be the main focus of this presentation. I'm hoping to keep it lightweight. It's going to be a mix of theory and some practical examples, but obviously reasonable within 20-25 minutes. And my name is Eve Reitzer, and currently I'm a technical consultant at Protegrity, company that does data security for enterprises. And I've been working professionally with Hadoop for the last 4 years, on and off, let's say. And this is what I prepared for today. Let me just move to the agenda. We're going to look at what is Hadoop and what's the rationale for this technology, why it was developed, and what sort of problems does it solve, also how. Then we'll talk about MapReduce. This is the first computing paradigm on Hadoop. So interesting to learn about it. Then we look at different ways of data processing on Hadoop. And then finally, I have a small section on how is Hadoop utilized in today's applications. First of all, what is Hadoop and why is Hadoop? You might have come across the logo before or the name before. Hadoop is essentially an ecosystem, right? It's a collection of services, collection of technologies. Some of these I actually marked here on the slide, and some of them you'll see in action today. But it's important to know that although there are some core components to Hadoop, some of these technologies are in a way plug and play, so that you can, for example, decide how you want to store the data. You can decide what technology to use to process that data, whether to put security on top of that, etc. And I think the big takeaway here is that Hadoop is not just one technology; it's an ecosystem. The logo the logo itself and the name doesn't really mean anything. There's actually a funny story behind it because the name and this yellow cute elephant comes a representation of a toy that Doug Cutting's son, one of the inventors of Hadoop, was playing with. And Doug Cutting thought, actually, this is a good name because it's simple, it sticks, and it means nothing. So why not use it? Just like Google, right? So this is where it comes from. It's not an acronym. It doesn't mean like distributed something, whatever. It's just a name of a toy. And the reason for Hadoop is essentially this: data. Due to the explosion of web-based services, unstructured data, social media, mobile computing, IoT, the amount of data to be handled has increased from terabytes to petabytes to zettabytes of data in just 2 decades. And I think all of us that are in this call, we all know that how unprecedented growth this is. I think we've all seen it in our professional lives. And so the problem with this is that even though we've got way better with being able to store this data, the access speed, so the rate at which the data can be read from drives, hasn't really kept up with the rate of innovation. And so this is not optimal because now we have all this big data that we potentially want to analyze, that we want to see some interesting insights in, but we don't really have the means to do it. And so this is the core problem that Hadoop approached to solve. And so the solution is the following, and this is the base architecture of Hadoop, in fact. Since it takes a long time to read data from a single drive, how about we reduce this time by spreading this file? Imagine I have a 1 terabyte file. By spreading it across, 100 drives, and then reading the data from these drives simultaneously, then we can cut the time of read incredibly. And so this is the core architecture of Hadoop, getting rid of this single central point of storage, and instead using the local disks of each machine to store the data. And so in this architecture, no machine has a complete view of the data, but we're no longer bounded by this I/O problem. And in that sort of architecture, you can also essentially scale indefinitely. You can scale linearly the system. And in real applications, there are thousands of computers. The Hadoop clusters can consist of thousands of computers, tens of thousands, because of this functionality. And what I've been talking about so far is this basis of Hadoop distributed file system, HDFS. When the files are put on the system, this is how it looks like. Every file would be split into large blocks. You can define the sizes, but the standard is, I think, 128 megabytes or 256. And these blocks are stored in the system. Also, there's always going to be copies of these blocks on different nodes in the cluster. So with this sort of architecture, the first thing we're doing is we're enabling this parallelism that we've been talking about before, but also we're making sure that the system is fault tolerant. I forgot the word. So because in that way, if one of the disks fails, you always make sure that there's a copy of this data living somewhere else, and your processing can pick up anytime. Now, the problem with this system, though, is since the data is spread across the cluster, how do we get this overall view of data? I can't just go to one machine because I will never know, for example, what the total number of my customers. This machine would only know a part of the story. So this is the question. How do you combine data in a distributed system like HDFS? To deal with this problem, and this is the original first computing paradigm on top of Hadoop, the inventors of Hadoop came up with this idea of MapReduce. MapReduce is called like that because it essentially does two things: map and reduce. And this is what you see here is a conceptual diagram. I'll show you an example later. But essentially what MapReduce does is it takes some input data, it gives that part of this input to every node, to a couple of nodes, and each of these nodes get the same function. They process this function on this data, on the data they have. Then the output is sent to reducers. Reducers then run some sort of function, potentially do an average or do a total count of all these occurrences. And then finally, they write the output back to HDFS. So there are essentially these two main phases, mapping and reducing. If you want to have an example, take a look at this. Imagine we are some sort of a commercial, maybe an e-commerce, maybe a Tesco, and we have all this information about what sort of fruits our customers like, and we want to know, what's the total sales of these fruits across the last year. So we have some input data, and the first thing that's going to happen is that my input reader will divide this input into these input splits, and each of these splits will be assigned a map task, as I was talking about before. And here at the map phase, what's going to happen is that each of these occurrences, I have to define it in the function, but what my function does is it assigns a value to each of these keys being the fruits. But for example, my first input split, I know I have one apple, one orange, and one mango, and that's it. This is what this part of the function does. This information is being computed, and now this is after a map phase finishes. The data is sent to reducers. But before this happens, there's a very important phase being shuffling and sorting this information. So that the way we send the data to reducers, it's also pretty smart. So, for example, all my apples would go to a specific reducer program. That the only function of this program then would be to count the total number of occurrences they have. You don't need to do any sort of specific, computation. So what you see here is my input for reducers. Then reducers kick in. They do a total sum of the fruits they have. And then finally, after this, the data is written to an output file, say in HDFS. So this is how a sample MapReduce program would look like. Now let's have a look at it in action. I've also prepared an example for you. First of all, I'll show you what data I'll be working with. So I downloaded it from the web. It's actually just 10 megabytes. So not the biggest file, but this is the complete works of William Shakespeare. And what we're going to do is we're going to count the number of words, of each word occurrences in Shakespeare works. This is my MapReduce program. So what you see here is actually what will be interesting for you, I think, is to see that there are two main parts. This is my mapper function, and this is my reducer function. And this is important because with MapReduce, you have to define that. You have to define it every time, what you want your map to do, what you want your reducer to do. Now, I'm going to move on to my Hadoop cluster and run this function on the complete Shakespeare works. Let me open that. And I think I'm in the right folder, but let's check. Yeah, so as you see, I have my Shakespeare text right here. Now, the first thing I need to do is I'm going to move it onto my HDFS because it's on my local drive. Nice. And one thing you'll notice is that these commands are very similar to standard Unix. Now, I'm going to move where my Java function is and run that function. Here, as you see, I'm calling my word count jar, and then I'm also saying use this information as an input and write it here as an output. Now, my MapReduce already started, and
can you guys hear Eve? I don't really.
Interesting results if you use like 1 million megabytes file. However, you see this information here. You can also in your function you can decide how many mappers, how many reducers you want to have, and also a lot of other stuff is configurable. So my MapReduce finished. Now we can take a look at how the output looks like. Actually, here I'm just taking a look into the output folder, and as you see, I have processed this file. This is where it lives, and now I can open it. I mean, I've already written these functions beforehand, but what this does is, as you know from Linux, this just opens the file, and I'm going to sort it by the number of occurrences. So we'll see the most popular files on the top, and then just return 100 of them. And as you see, that's my result. That's pretty simple, to be honest. That's a pretty cool application. Not a perfect function because, as you see, my some commas and some asterisks were picked up, and also some words that we're not very interested in, like a or in, etc. But you can already see some interesting results, such as the word love has been used pretty much a lot of times. Lord as well. So, of course, this can be improved, and all the sort of things can be defined in the mappers or in the reducers. So, for example, ignore whether something is uppercase or lowercase, or remove these sort of stop signs. But you have an example of how MapReduce looks like and works. Now, let's go on. One of the things you would have noticed by now is that, well, this was Java, and that was a very simple application. I was essentially just counting the word occurrences, and that was already a massive file because this is how you write Java in the end. And this is the problem with MapReduce. To do even a simple thing, you have to create a massive Java code. If you want to do something else with this file, after this word count, you want to do some sort of other data processing, you have to write another MapReduce and wait for it to finish. And so the people who usually would do data analysis are not really Java developers, if you think of that. So this is a big problem with Hadoop. And so soon enough, there were some processing upper level abstractions built on MapReduce to sort of ease that pain on programming in Java and enabling data analyst teams to use the power of Hadoop. And some of these are, I'm going to talk about some of these. There's also more, but these are the ones that are, I think, most emblematic for Hadoop. Starting with Pig. Pig is not exactly in use anymore. Maybe in some old Hadoop clusters, yeah. But you already can see like what sort of things it allowed people to do. It's coded some of the keywords, such as load data, output data, or do a maximum, do an average, so that you didn't have to write all these pieces of code. It was just really simple to use. And it was also pretty funny because it was called Pig. The CLI was called Grunt. The language was called Pig Latin. So I actually quite like this example. And Pig was developed in Yahoo, I believe. An alternative, more or less the same time, I think, was Hive. That was developed on Facebook. And Hive is essentially structured very similar to your typical SQL. In fact, this is an ongoing development, and the current SQL of Hive looks very, very similar to what you're used to in your typical relational databases. You have not only the standard SQL, but you have also like window functions, you have rolling averages, all these sort of cool things that you can do on a standard database. And I think, but of course, under the hood of all these applications, you still had MapReduce. So every time you do something with them, there's a MapReduce job kicking off. And I wanted to show you an example of how to do data analysis with Hive, just so you get a gist of how it looks like. This is my my Hive. This is Beeline. This is how the CLI is called. And what I'm going to do is very simple. I just wanted to show you how to create a file and what sort of operations trigger MapReduce, what sort of doesn't. So as you see, standard SQL, create table, and you define your schema. You say, okay, it's going to have some information about the customers, whatever. I just have a file like that, so I used it. You also define how the data is stored. And this is actually I wasn't thinking of talking about it, but this is actually an interesting bit because you can also, of course, you can use different types of underlying storage. You can store data as columns, you can store data in JSON, what have you, right? This is not very strict. You can also use your own serializer, deserializer, etc. So let me create a table and load the data into it. In fact, my data lives on my local drive. But it could easily live on Hadoop. And now I just wanted to show you like top 10 rows, like what's in that data. And you should be surprised here because why is this so fast, right? Then I tell you that all this runs MapReduce underneath. Well, it does, but this information is a simple read of the file. I did absolutely nothing in my select statement other than selecting this information, so selecting top 10 rows. Nothing that had to be processed. Now, take a look at what's happening when I run a very simple transformation, such as where. Like, this is some customer data, and I would just do like, where region is Florida, let's say. Made a mistake? Okay, I need to remove the limit. And there we go. This is already, this little pause already means that MapReduce job is starting. And I will let it running, but I think you see what I'm trying to get to. When you do a data analysis, you don't really want to wait for your query a couple of hours to finish. Data science or data analysis is in its core very iterative or an interactive. So very often you do ad hoc queries. You just want to check one thing. And Hive, as well as Pig, is a tool created for ETL, for like batch data processing that's slow, that you actually don't care about. You can leave it running overnight, and that's cool. So it's not really an optimal tool when it comes to data analysis. And what you see here is I copied it from the internet. It's a slide from is a photo from a Presto in fact, back then, the ability to run, say, 6 Hive queries a day, this is still better than no queries, to be honest. So I think at the beginning, Hive was actually already pretty much a big step. However, with time, of course, people started to think, okay, how can we speed these things up? Maybe MapReduce is not the only way to go. And so the outcome of this thinking was creating alternative data processing engines on Hadoop. 2 of them I've marked here, Spark and Impala. And I wanted to talk about one of them in more detail, namely Spark. You might have heard the name because Spark is incredibly popular. Spark is it's an alternative to MapReduce. And the big difference, without going into details, is that it can process data in memory. So you don't have this batch-oriented system that has to write files to this, then read from them, etc. Here, Spark can cache data in memory, and that makes it so much more powerful. It's also, the execution is more optimized. Another thing that makes it a fantastic technology and very useful for specifically data analysis is that you have a choice of languages in Spark. You can call them Scala, the original language. You can use Java if you like Java, or you can use Python, the de facto language of choice for data scientists. But there's also some libraries for R on Spark if you want to use that. So it's pretty flexible. It also combines SQL, so you can run some SQL with it. You can process streaming data, and it also has a really good machine learning library. So you'll see here. I think I also opened my email in the background, but regardless. So there's also already, a couple of really cool algorithms you can use. You don't have to create from scratch. So back to the presentation. I think I also wanted to show you an example of Spark. We're basically going to do the absolutely same thing we did with MapReduce on the same file, but this time in memory. That's my Spark. As you see, I'll be using Scala for that exercise, but the code is really simple. So I'm going to use as input, I'm going to use my the same Shakespeare complete works file. And this is actually, you can see it here. This is created on RDD. This is like a logical collection of files in Spark language. And I'm going to, this is the actual function. So I'm going to essentially count the number of occurrences of each of the words in that file. Done. That was it. So a massive difference. Now, just to show you that this was successful, I'm going to print my word occurrences. And here they are. Now, I didn't sort them, but you get the point. So way better way to really, especially for data science, a way better way to work with Hadoop. Now a couple of words about Hadoop in real environments. This is something I really wanted to mention, like Hadoop versus relational databases, because it comes up very often. I would say that Hadoop is usually, besides like hardcore applications, but it's usually used as a complementary technology to RDBMS. So the reason for that is that if you think of that, these technologies actually can work very well together. So your typical RDBMS by default will have like a very strict schema. You would have to know like what sort of files, what sort of data are you putting in before you put them into the database, because it follows because it has a certain schema, and the schema is very rigid. And the problem with that is, of course, maybe we are processing files before they go to the database so much that we're cutting out some of the information that's potentially good for analytics, and we don't even allow it to get in. Also, of course, the application change, especially in the modern world, and for RDBMS can struggle with accommodating for these changes. So, however, there's of course massive gains when you're using RDBMS. You have your caching, you have your indexing. The queries are incredibly performant. And on the other hand, you have Hadoop. that, if you use, for example, MapReduce, it's not going to be as performant as an RDBMS will be. But if you think of that, there's also some clear benefits here, besides the price, which I'm going to talk about later. But first of all, Hadoop allows you to put into HDFS any file you have. You don't have to care about the schema. And that means you care about it at the time of the actual analysis. And this is potentially enabling a lot of applications, because maybe when you're gathering your files, you don't really know what you want to study. You don't know what's interesting in it. So you want to do this sort of discovery at the beginning. And then because you care about the data just at the moment when you analyze it, you can also pick a tool. You can also pick your favorite data processing tool at this moment. It also, of course, Hadoop has this incredible scalability that allows it to put the properly big data as well. So I think there's advantages and disadvantages on both sides. And this is, I think, what's typically used in companies to what I could see. And I see specifically 4 architectural patterns for Hadoop use, generally speaking. So on one hand, it's very typically used as an active archive. This pattern talks about, how the advantage or the benefit of a single data point decreases over time. So it doesn't sometimes make sense to store all this information we have in RDBMS and fill it up. It might just make sense to just store some averages and archive the rest of the data, the single data points. And this is essentially this pattern. So in your RDBMS, for your data analysis, you store the information that you need to store, and you offload everything else to Hadoop. And if you need to access it, you can access it. But clearly, this just saves money, because to scale a commercial relational database, Oracle, Teradata, Microsoft, to the level that Hadoop can scale on commodity servers, is going to cost you basically millions. So Hadoop is like this sort of cheap but incredibly attractive alternative in these cases. And then there's also the pattern of offloading ETL jobs to Hadoop. ETL, if you don't really know the database terminology, but this is the phase of data processing before the data is really accessed for analysis. So it could be some transformation, cleanup of the data, some typical stuff that you do before the data lands in the data mart. And Hadoop is actually perfect for that, because if you think of this, Hive has already these incredible SQL capabilities, and it can easily process this data, these data-intensive workloads. Usually, you can easily process them. You don't really care about the speed of this process going on either. So it's really perfect for ETL offload. Similarly with some query push down that I've also noted. And these are the cases when you're, for example, dealing with very, very big files. Many commercial databases, if not all of them actually, can already deal with, for example, some unusual data formats. But doesn't mean that they would, or that it doesn't mean that this is the best case for using RDBMS. So these sort of applications, when you have an unusual structure or an unusually big file, it's also really good for Hadoop, because there you write, a specific job, it gets processed in Hadoop, and everybody's happy, and RDBMS is not overloaded with processing. And then finally, potentially the most interesting use case is an R&D lab, using Hadoop as this, as a data lake, where you put any sort of data you can, and you do your discovery. You look at what is actually interesting in this data. Basically, a paradise for data scientists to build on top of Hadoop. Of course, there's a couple of risks associated with this pattern, as the fact that we can put in any sort of data. It doesn't mean that we should, but it's a very, very fun use case in that case. And so that is the end of my session. I hope you liked it. I hope it was entertaining, but you still managed to learn something. Let me know if you have any questions, and also contact me if you can add me on Twitter or go to my blog if you like. So,
thank you. That was really informative and interesting. Thanks for the effort and the presentation. Now we open the question round, so everyone feel free to ask Eve some questions that you have regarding Hadoop and maybe the technologies associated with it. So anyone want to go forward? I'm gonna you have to unmute and then you can ask the question. Okay, so I will ask the first question in that case. I just see Vikas just wrote a question. So Vikas is asking, it's still not very clear how the big file is divided into small pieces. What can you say to that?
Yeah, so you'd normally define this on Hadoop. So I don't know if you see my screen now. I'm trying to change the slide, but I never can. So at the beginning, where the file is ingested to HDFS, you have a setting that says like how big you want your data blocks to be. And I'm trying to get there. Here it is. Okay, I'm just gonna close maybe this. So, well, the files. Oh yeah, there we go. The files essentially split into data blocks. That's basically it. And then you define how big you want your data blocks to be, and these data blocks are then spread across the cluster. So every time a map reduce job runs, it will take each of these. It's called input split, but it's a logical representation of a block and process that certain block.
Okay, I hope that clarifies it to a certain extent. So my question would be about the cache in Spark. So usually that doesn't that take? So that's an in-memory cache, or where is the search result cached in that case, and how efficient is that, and how often? I assume it's also depending on the system you're using, but isn't that very intense to have all these very expensive to have all these data in the cache and in the memory?
I mean, like, absolutely. Like, this is obviously memory bound. If you don't have enough memory, you're not going to have a problem, because Spark is going to write data to disk. But it still speeds up the whole job incredibly, because you don't now with MapReduce. What happens is that every mapper actually writes the intermediate results to disk, and then picked up. So if you keep all this data in memory, this is a massive gain for the system. But of course, this is memory bound. So if you don't have enough memory, your Spark jobs won't be as incredible as advertised.
Okay. Maybe a simpler question also. At what point do you think a traditional database, or let's say like a schema-less database like Mongo, and just queries on that are not enough? Or where's the breaking point where you would suggest the setup with Hadoop and Spark?
I think, like, if you talk about NoSQL databases, I think they simply serve a different purpose, really. Because if you think about these patterns for Hadoop that I listed, there was a lot about ETL, right? There was a lot about these batch processes, besides the R&D lab. But Mongo and other NoSQL, these are good applications where you want to have fast writes and fast reads. So very different problem. If you think of that, like the problem that is very common, for example, for e-commerce stores. Also, another thing is that Hadoop, with Hadoop, this is still you're going to have a single answer after all this processing. With NoSQL, this is not necessarily so. So I would just say, like, these are very different applications. I wouldn't say one is a substitute of another.
Okay. If anyone else has a question.
I was having a question. Can you hear me okay now?
Yeah.
Awesome. So I was just wondering if you can tell me any company or any website which is using Hadoop at this moment, because I'm not very sure where can I use Hadoop as a web developer. Probably there might be some other implementation somebody may be using.
Mm. So, I mean, Hadoop was initially developed at like these big search companies. So Facebook, Google, Yahoo, all of them used it. Now, in my professional world, the things I see, it might be a very biased view, but a lot of banks use Hadoop. A lot of these companies that have a lot of data. It's very rarely used if, for companies that don't really deal with massive data volumes, because there's rarely the point. And it's also very often used as a cheap alternative to RDBMS. Of course, it doesn't do all the things that RDBMS does, but you can use commodity servers, so that's a better sort of alternative. Some e-commerce also use it, not for handling transactions, but simply for gathering data and analyzing data. So I think eBay, I would think that they have it. I know an equivalent of eBay, a Polish, like sort of East European company, Allegro, also uses Hadoop.
Okay, cool. So it's like more for analytics, right? And not for the actual purpose of the commercial website. Like Google would use it to display their search results.
Yeah. For example, a lot of things that need to be batch processed, ETL. R&D labs also a pattern, but mostly for the purpose of gathering these masses of data.
Got it. Thanks.
All right. Any more questions? Maybe my last question to finish this is, how's the market developing in that area? I know that might interest some people here. Is it reasonable to become a Hadoop Spark expert, and that demand rising? And is it what are the best learning resources for freelancers who want to switch into that area?
So I think yes, but I think the answer could be actually quite complex, because if you think about the Hadoop adoption, it seems like it's no longer just the keyword. And from my own background, I can see how companies are more brave, let's say, or more daring, and they apply Hadoop, they try to they really use it for their own in their own organizations, and it's not something like they fear anymore. So there's still, I think, a massive demand for Hadoop developers. But on the other hand, if you think about like a bigger context, and where, for example, data privacy laws are going, it's say 5 years ago, when I started to look into this topic, everybody was like, yeah, you should gather data, you should get as much as possible, and then do these crazy analytics, what have you. And now everybody is like, actually, maybe we don't need to gather this data. Maybe this is actually scary if we gather this data. And maybe this is actually a potential security breach just waiting if we do that. So that sort of thing, you have to keep in mind. I still think there's always going to be applications of Hadoop, and it's still a really hot topic. Then on the side of Spark, that's also a different story. And I think this also comes back to the previous question about, who uses it. Because Spark is in a way a different paradigm, and you can also uncouple Spark from Hadoop, which is from HDFS, which is another interesting thing. And Spark is really great for machine learning applications, and we all know that AI and machine learning are like the hottest topics now. So definitely Spark, machine learning, Python. This is like where I would put my bid if I could.
Okay. I agree. We also have some Hadoop projects running at the moment. So actually, one of our freelancers has a PhD in data science and will follow up pretty soon with a detailed Spark intro. So that might interest you guys too. I will keep you guys posted in the Slack. Thanks again, Eve, for this presentation, and thanks for sharing your knowledge. We will share this video after processing it in our YouTube channel, and get back to you with some interesting other skill sessions that you can join maybe later in the future.
Cool. Thanks a lot. Thank you for having me, and have a good evening.
Sure. You too. Have a good evening, guys. Bye-bye.
Good evening.
Bye-bye. Good evening.
Thank you. Bye.